It's been called the most studied world in the universe after Earth. For over half a century, we've looked at it, landed on it, and sent countless machines to circle it. The moon, that cold gray sphere hanging in the sky, has been mapped, scanned, sampled, and photographed more than any other body in space. And yet, after all that effort, it still refuses to give up one of its most important secrets. Because buried somewhere in that dust, hiding in shadows colder than Pluto, and maybe even scattered across the sunlit plains, is something no one thought we'd ever find there: water. And not just a few drops. If some of the readings are right, there could be hundreds of millions of tons of it, enough to build bases, refuel rockets, and change the future of space exploration forever. But here's the strange part. Every time we think we've finally solved the mystery, the moon throws us another contradiction. Data that says one thing, landers that show the opposite, craters that should be full of frozen ice, but look like nothing more than dust. It's a riddle that's been unfolding for decades, and the deeper we dig, the stranger it gets. It started quietly, almost as a footnote. The year was 1976. The Soviet Union launched a robotic lander called Luna 24. Unlike earlier missions that simply touched down, this one had a specific job: drill beneath the surface and bring a sample back. It bored 2 meters into the lunar soil, pulled out a slender tube of dust, and sent it back to Earth. The total weight, just 170 grams, about the size of a baseball dot. At first glance, nothing seemed unusual, until scientists looked closer. Inside that narrow tube was something shocking: a trace of water. Roughly 0.1% of the soil contained HOO, and strangely, the deeper they looked in the sample, the more water they found. This should have changed everything, but instead, it was brushed aside. The easy explanation was contamination. The water, scientists said, must have come from Earth. Maybe it leaked in through the equipment. Maybe it got mixed during handling. Either way, it couldn't be real. After all, the textbooks were clear. The moon was dry. Everyone knew that DOT and Luna 24 wasn't the first time either. Even during the Apollo missions, astronauts had brought back rocks that hinted at hydrogen-bearing compounds. But once again, the traces were dismissed. Interference, they called it, a glitch, a fluke, nothing serious. So for decades, the signs sat ignored in lab reports and archives, hidden in plain sight. What no one realized then is that those tiny ignored clues would come back, and when they did, they would shake everything we thought we knew about the moon. But before that happened, the mystery had to shift to an even stranger place: the shadows. Imagine standing at the edge of a crater near the moon's south pole. Around you, the ground is lit by the low sun, but at the center of the crater, there's nothing but darkness. Not dusk, not night. True, absolute black. A shadow that hasn't moved in billions of years. These are the permanently shadowed regions, or PSRs, because the moon barely tilts on its axis. Just 1.5 degrees sunlight at the poles skims sideways. Across the horizon, deep craters never see a ray of light. Inside, the temperatures plunge below -240 degrees Celsius. That's colder than Pluto, colder than Uranus and Neptune. In fact, some of the coldest places we've ever measured in the entire solar system exist not on the edge of deep space, but right there, a few days' journey from Earth. In an environment like that, ice could survive forever. No melting, no sublimation, no sunlight to drive it away. And that's when scientists began to wonder, what if water really did exist on the moon? Not as contamination, but locked away in these frozen basins. It made sense. Billions of years ago, comets and asteroids carrying water would have slammed into the moon. On the sunlit plains, the water would boil off immediately. But in the PSRs, the ice could have drifted down into the darkness and stayed there untouched for eons. This was more than just an interesting theory. If it were true, it meant the moon wasn't just a dead rock. It meant it had resources, and that changed everything. Suddenly, the race was on to prove it. The first major step came in 1994, with a mission that wasn't even supposed to be looking for water. Clementine, a joint project between NASA and the Department of Defense, mapped the Moon's surface with unprecedented detail. Among its findings, confirmation that those polar craters were permanently shadowed, it couldn't see inside them. But it proved the cold traps existed. Then, in 1998, Lunar Prospector was launched with a clear goal: search for signs of water. Using neutron spectroscopy, it detected strong hydrogen signals near both poles, especially in those shadowed craters. The data suggested something astonishing. There could be anywhere from 10 million to 300 million metric tons of water ice hidden across the lunar poles, enough to change the trajectory of human spaceflight forever. But there was a catch. Hydrogen doesn't always mean water. It could also mean hydroxyl compounds or hydrogen locked inside minerals. The instruments couldn't tell the difference, so once again, we were left with a frustrating half answer. Something was there, but was it really ice? To find out, scientists decided to try something new. If orbiters couldn't see into the shadows, maybe a crash would dot it. Sounds crude, but the idea was simple. Smash a spacecraft into a crater, kick up a plume of dust, and analyze it for signs of water. In 1999, Lunar Prospector itself was sacrificed this way. Steered into a polar crater, Earth-based telescopes watched the impact closely, hoping for a glimmer of ice crystals in the plume. Nothing. The test was inconclusive. A decade later, Japan's Kogia orbiter tried something similar in 2009. Once again, no useful results. Just dust. But then came LCROSS. NASA launched it in 2009 with one mission: prove once and for all if water ice exists in a permanently shadowed crater. LCROSS didn't crash alone. It brought the upper stage of its rocket along as a battering ram. First, the empty rocket body slammed into the crater Cabeus at over 9,000 kilometers per hour. Then LCROSS itself flew through the debris plume, analyzing it in real time before colliding a few minutes later. This time, it worked. Instruments detected water vapor. Not just a trace, real, measurable water, along with hydrogen, methane, and ammonia. For the first time in history, we had direct proof. The Moon wasn't bone dry. There was water hiding in the shadows. For a brief moment, it felt like the mystery was solved. But, as always, the Moon had other plans. Because while scientists celebrated LCROSS's success, other data started raising new questions. NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1 began detecting faint water signals across the entire surface of the Moon. Not just in cold traps, not just in shadows. Everywhere. Even stranger, the signals changed with time of day. Around lunar noon, when the surface is hottest, the water seemed to vanish. By evening, when the ground cooled, the signals returned. It was as if the Moon was sweating, losing and regaining water molecules in a daily rhythm. How was this possible? The Moon has no atmosphere, no clouds, no weather, no way to trap water vapor. And yet, something was clearly happening. Two theories emerged. 1. Micrometeorites constantly striking the surface were delivering water or knocking it loose from minerals. 2. The solar wind itself, blasting hydrogen particles into oxygen-rich lunar soil, could be creating hydroxyl and water molecules. Either way, the conclusion was shocking. The Moon wasn't just hiding water in frozen craters, it was actively holding on to trace amounts almost everywhere. This completely changed the game. Suddenly, it wasn't just about building a base in one special location. If water was widespread, the entire surface might become usable. But when the next lander finally touched down near the South Pole, the results would leave scientists more confused than ever. In 2023, India launched Chandrayaan-3 with one bold objective: land at the South Pole and confirm the presence of ice. The lander Vikram carried a small rover called Progyan. Together, they were equipped with instruments capable of directly analyzing the soil. For weeks, they crawled across the lunar terrain, firing lasers into rocks, blasting alpha particles, and reading chemical fingerprints. They detected aluminum, iron, calcium, chromium, even titanium, all crucial for understanding lunar geology. But one thing was missing: hydrogen, and without hydrogen, there's no water. This was the exact region that maps and orbiters had labeled the most promising. Decades of data suggested it should have been the wettest spot on the moon. But the rover's direct scans found nothing. Dry soil, no hydroxyl, no ice. Had we been wrong all along? The contradiction shook the scientific community. If orbiters saw hydrogen, why didn't the lander? Had the signals been misinterpreted? Or was the water simply deeper, out of? Among Vikram's instruments was a simple thermal probe, designed to measure how heat moved through the soil. It inserted itself just a few centimeters below the surface, at the top. Under direct sunlight, the temperature was around 60 degrees Celsius, but only 8 centimeters down. It dropped to minus 10 degrees Celsius. That's a massive swing in such a short depth. What it revealed is that lunar regolith is an excellent insulator. It traps heat and cold, meaning just beneath the surface, temperatures could stay stable enough to preserve water ice, even if orbiters can't see it and landers can't reach it. In other words, maybe the ice is there. We just haven't dug deep enough, and suddenly, all the contradictions made sense. Orbiters detect signals from deeper layers. Impact plumes reveal hidden water. But shallow probes, they come up dry. It wasn't that the moon was lying. We just weren't looking far enough beneath its skin. For decades, the question of lunar water was treated as a curiosity, something for geologists and planetary scientists to argue about. But not anymore, because water isn't just a science problem. It's survival. Every liter of water launched from Earth costs thousands of dollars. But if astronauts can find it locally, they can drink it, use it for cooling equipment, grow food, even split it into hydrogen and oxygen for rocket fuel. Suddenly, the moon becomes not just a destination, but a gas station, a staging ground for Mars, for asteroids, for the rest of the solar system. And beyond science, there's geopolitics. The first nation to control a stable source of lunar water won't just have bragging rights. They'll have power. The ability to set the rules for who goes where, who builds what, and who controls the future of space. That's why the South Pole is getting crowded. That's why missions keep circling the same dark craters, because somewhere, down there, hidden in the shadows, is the key to opening space for good. This is where things took a turn no one saw coming. While most of the world imagined water locked away in eternal shadows, NASA's Moon Mineralogy Mapper, an instrument on board India's Chandrayaan-1 orbiter, began detecting faint but unmistakable signs of water molecules across the sunlit lunar surface. At first, scientists thought it had to be a mistake. The daytime surface of the moon gets hot enough to boil water away instantly. How could water possibly survive there? But the data kept coming. The signals were real. More curious still, the strength of those signals changed with time. At lunar midday, when the sun's heat was most intense, the signals weakened or vanished. At night, as the surface cooled, the signals returned. It was as if the moon was literally sweating, releasing water when it heated up, then reabsorbing it in the cool. The theory was radical. Micrometeorites striking the surface could release tiny pockets of trapped water, or the solar wind itself might be bombarding the moon with hydrogen that bonds with oxygen in the soil to form hydroxyl and water molecules. If true, this meant the moon wasn't just passively holding ancient ice. It was an active system, constantly creating, losing, and recycling water in real time. That changed the game completely. Transition, and then came the boldest test yet. A lander touching down at the South Pole itself, but what it found shocked everyone. In 2023, India made history. The Chandrayaan-3 mission successfully soft-landed near the lunar South Pole, the very place scientists believed was the richest reservoir of lunar ice. For decades, orbital data suggested hydrogen was concentrated in this region. It was supposed to be the moon's wettest spot, but when Chandrayaan-3's instruments got to work, the results were baffling. They detected metals like titanium and aluminum, they measured surface temperatures, they probed the soil. But the expected hydrogen signals simply weren't there. No hydrogen, no hydroxyl, no water. This was a bombshell. The very location hyped as the moon's ultimate ice mine turned out bone dry at the surface. Scientists were forced to confront a devastating possibility. Maybe the orbital data had been misinterpreted all along. Maybe the hydrogen signals were caused by something else entirely. The contradiction couldn't have been sharper. For years, satellites told us one story. Now, a lander on the ground was telling us the opposite. For India, it was still a triumph. The first ever successful landing at the South Pole. But for the scientific community, it was a puzzle that made the mystery deeper than ever. Transition, but before anyone could declare the mystery solved, one final reading from Chandrayaan-3 revealed a twist that flipped the story yet again. While Chandrayaan-3's surface tests found no water, one of its probes delivered a clue too big to ignore. As the instrument measured heat flowing through the lunar soil, scientists noticed something strange. The surface temperature dropped off far more sharply than expected. Just centimeters below the regolith, the heat was gone, shielded away as if by insulation. This discovery was groundbreaking. It suggested that the lunar soil acts like a thermal blanket, protecting anything beneath it from the harsh heat of the sun. And what could be hiding under that protective layer? Ice. In other words, the lack of water on the immediate surface didn't mean the moon was dry. It could mean the water is simply buried just a little deeper, safe from detection by surface instruments, but still real, just out of reach. This would explain decades of contradictions. Orbiters detecting hydrogen signals from above, but landers scraping only the topmost dust and finding nothing. The water might be there all along, simply hidden under a thin cover of dry regolith. If true, this changes everything. It means the moon isn't lying to us. We've just been looking in the wrong place. At first glance, you might ask, why does any of this matter? So what if the moon has a few frozen patches of water, or none at all? But the truth is, water on the moon is the difference between a base that's temporary and one that's permanent. For astronauts, water isn't just for drinking, it's survival. Split into hydrogen and oxygen, it becomes rocket fuel. Purified, it sustains crews, and in agriculture experiments, it could one day grow crops in lunar soil. A steady supply of water would turn the moon into a cosmic gas station, a refueling stop for missions heading deeper into the solar system. Without it, everything has to be carried from Earth. Every liter of water launched from our planet costs tens of thousands of dollars in fuel and infrastructure. That makes long-term human presence on the moon nearly impossible. This is why nations are racing to solve the mystery. The United States, China, India, and Russia are all planning new landers and rovers targeting the South Pole. NASA's Artemis program is specifically aiming to set astronauts down in these shadowed craters to test the reality of the ice firsthand. And there's a deeper layer. Some scientists believe that if lunar ice exists in abundance, it might not just be a tool for human survival, it could be a time capsule of the early solar system. Frozen billions of years ago, untouched for eons. These deposits might hold pristine samples of ancient comets and asteroids that bombarded Earth long before life began. Studying them could reveal how water, and maybe even the ingredients of life, first arrived on our planet. Imagine that. Hidden in the dust of the moon might be the origin story of life itself. But there's a catch. If that ice truly exists, it may be far more fragile than we thought. The first spacecraft to dig, drill, or melt it might contaminate or destroy it forever. It's not just a resource, it's a one-of-a-kind archive, and once it's gone, it's gone. This raises uncomfortable questions. Do we harvest it too? Build our future, or preserve it to understand our past? That's the tension driving this mystery, and it's why every contradictory reading, every dry crater, and every hidden signal isn't just frustrating, it's urgent. Transition. So where does that leave us today? After half a century of searching, the moon's answer is still the same: not yet. Asterisk, for more than 50 years, the search for water on the moon has been a story of triumphs and disappointments. Satellites have whispered promises, crashes have teased fragments, landers have contradicted decades of data, and yet, the answer remains out of reach. The moon, it seems, is guarding its secret with patience. Think about it. The first Apollo astronauts looked up and saw only dust and rock, a barren wasteland, hostile and dry. But then came the whispers of ice in shadows, then faint traces across the surface. Then the idea that the moon might even create water anew each day. And just when the mystery seemed within reach, Chandrayaan-3 reminded us, not so fast. It's a reminder that discovery is never straightforward. Nature doesn't hand us the truth on a silver plate. It teases, it hides, it forces us to dig deeper, literally and figuratively. And so the moon waits, silent, patient, orbiting above us as it always has, holding on to its last great secret. But make no mistake, humanity is not done asking. With new rovers, new landers, and soon humans returning to the lunar surface for the first time in half a century, the question will be asked again and again, is there water on the moon? And when the answer finally comes, it won't just reshape our plans for space exploration. It may rewrite our understanding of how Earth itself became the blue planet in the first place. Until then, the moon remains what it has always been, a mystery hiding in plain sight. The mystery of water isn't just about H2O molecules. Lunar soil itself has become a puzzle. For decades, scientists assumed the regolith, the layer of dust and rock fragments covering the moon, was uniform, inert, and lifeless. But data from Chandrayaan-3, combined with previous landers and rovers, shows otherwise. Instruments detecting elements like titanium, aluminum, calcium, and iron revealed uneven distributions, suggesting the moon has a more complex geological history than imagined. These variations could indicate ancient volcanic flows, asteroid impacts, and even localized chemical reactions that alter how water and hydrogen behave underground. Some researchers have speculated that certain minerals in the regolith might actually trap water molecules, holding them in a form that standard instruments can't detect. In other words, water might be present but chemically hidden, locked inside minerals, waiting to be released under the right conditions. Transition. If the soil itself can hide water, then maybe the mystery isn't just where to dig, it's how to recognize what you find once you do. The permanently shadowed regions, PSRs, remain among the coldest places in the solar system. Temperatures plunge below -240, so colder than Pluto or even distant moons like Triton. Scientists call these regions thermal traps, where water, once deposited, could survive for billions of years. But the challenge isn't just cold, it's accessibility. The terrain is jagged, cratered, and dark. Sunlight never reaches these basins, which makes solar-powered rovers almost useless. Every landing and movement requires meticulous planning, precise timing, and backup systems. And yet, PSRs hold the key to unlocking lunar water as a usable resource. Even small pockets could sustain long-term human missions or fuel rockets for deep space travel. Transition. But what about the rest of the moon? The sunlit surfaces, the edges of craters, even slopes facing Earth. Could water exist there too? Early data suggested the sunlit regions should be dry as bone. Yet instruments like the Moon Mineralogy Mapper have detected faint signals of water molecules across these bright surfaces. This paradox puzzled scientists. Water shouldn't survive the heat. The leading theories involve solar-wind interactions. Hydrogen atoms from the sun may bombard oxygen in the soil, forming hydroxyl, and sometimes water molecules. Micro-impacts from tiny meteoroids could also release or deposit water. Interestingly, the signals change with the lunar day. Water molecules disappear in the heat of midday and return as temperatures drop in the evening. This lunar sweating hints at a dynamic water cycle unlike anything seen on Earth. It's subtle, molecular scale, but persistent. Transition. This discovery flipped the narrative. The moon isn't just a static desert, it's a subtle, active system where water moves in ways we're only beginning to understand. Every past mission contributed clues, even when they seemed contradictory. Apollo samples hinted at trace hydrogen. Lunar missions detected water deep underground. LCS-CROSS confirmed vapor in impact plumes. and orbiters like Chandrayaan-1 revealed surface hydroxyl. Taken together, the evidence tells a story of hidden, distributed water, partially frozen in craters, partially trapped in minerals, partially mobile across sunlit regions. Yet, our tools are still imperfect. Landers reach only centimeters below the surface. Orbiters detect signals but can't touch. And spectrometers can't always distinguish water from other compounds. Science, in this case, isn't about a single discovery. It's about piecing together decades of fragmented data into a coherent map. A map we're still drawing. Transition. And as we build that map, the stakes have never been higher, not just scientifically, but geopolitically and economically. The moon is no longer just a playground for scientists. Access to water is power. Countries are racing to stake claims, not in a legal sense, but through capability. Whoever develops the first reliable water extraction and utilization system gains a massive strategic advantage. NASA's Artemis program, China's Change missions, India's Chandrayaan-3, and private companies like SpaceX and Blue Origin are all circling the lunar South Pole. The race isn't about flags anymore, it's about infrastructure. Water means fuel, means bases, means long-term presence. This urgency affects mission design, funding, and international cooperation. Mistakes or miscalculations could mean billions of dollars lost or opportunities missed. It's a high-stakes chess game played on a gray, dusty surface 384,000 kilometers from Earth. Transition. And yet, even in the middle of this race, the moon continues to defy us, keeping its secrets buried just beneath our tools. What comes next? Scientists and engineers are designing rovers with deeper drills, smarter sensors, and autonomous mobility to access water buried under. Some plans involve robotic miners that could extract ice without human presence. Others imagine modular bases built around water-rich regions. There are also new orbital instruments that combine spectroscopy, radar, and thermal imaging to map potential ice pockets with unprecedented resolution. These tools aim to solve the biggest unknowns. How deep is the ice? How pure is it? And how accessible for humans? And beyond technology, there's the bigger picture. Every mission we send is a step toward permanent human presence on the moon, using local resources to sustain life and explore deeper space. Lunar water isn't just a scientific curiosity anymore. It's a cornerstone for humanity's future among the stars. Transition. Even with all these plans, one thing is certain. The moon will not make it easy. It has already taught us patience, humility, and the need for ingenuity. NASA's Artemis program represents the most ambitious step toward sustained human presence on the moon since Apollo. Unlike earlier missions that were short-lived, Artemis aims to place astronauts near the lunar South Pole for months at a time, with bases capable of supporting life using local resources, including water. The stakes are enormous. Extracting water in sufficient quantities could make lunar bases self-sustaining, dramatically reducing reliance on supply shipments from Earth. Every liter of water saved is thousands of dollars, thousands of kilograms, and countless logistical headaches avoided. But Artemis is also a test of technology and resilience. Landers must navigate the treacherous terrain of shadowed craters. Rovers must dig deeper than ever before. And all of it must be done with precision. One misstep could compromise years of planning. Transition. Even as NASA prepares to land humans, private companies and international rivals are already planning to stake their claims, turning the South Pole into a stage for the next space race. China's Change program has steadily advanced lunar exploration. With Change 5 and Change 6, China has successfully returned samples, analyzed the regolith, and now eyes the South Pole. Their strategy mirrors NASA's, but also focuses on long-term occupation. China is developing rovers capable of autonomous ice detection and extraction. Their goal is dual: scientific discovery and strategic positioning. Control over water resources at the South Pole could give China not just technological leverage, but geopolitical influence. This raises questions. Will the moon become a collaborative frontier, or will nations compete fiercely for access to resources? The answer could shape the next century of space exploration. Transition. While governments plan and compete, private companies see opportunity, not just in exploration, but in turning water into a commercial asset. Water on the moon is not just fuel and life support, it's a commodity. Companies like SpaceX, Blue Origin, and Astrobotic envision mining lunar ice, converting it into rocket fuel, and creating a refueling network in space. Imagine a spacecraft launching from Earth, topping up at a lunar depot, then continuing to Mars with minimal Earth-based supplies. That's the vision. It turns the moon into an interplanetary gas station, a concept that was pure science fiction decades ago. Private missions are already testing autonomous drills, 3D printed habitat modules, and in-situ resource utilization technologies. The success of these experiments could determine whether humanity colonizes space slowly and cautiously, or accelerates into a multiplanetary future. Transition. Yet for all these plans, one nagging question remains: how much water is actually there, and how accessible will it be when we need it most? One of the biggest mysteries is not the amount of water, but its depth. Surface probes often detect none. LCROSS plumes came from impacts that disturbed the first few meters. Chandrayaan-3 found nothing on the top layer but measured temperatures, suggesting ice could exist just below dot. If water is buried beneath even a few centimeters of insulating dust, it could remain invisible to our current instruments. That means every mission must dig deeper, design better drills, and develop sensors capable of detecting water chemically bound inside minerals. This is a subtle but profound realization. The moon's water might be hidden in plain sight, just out of reach, waiting for humanity to develop the tools to uncover it. Finding water on the moon isn't just practical. It's a scientific goldmine. Frozen ice trapped for billions of years could contain ancient molecules delivered by comets, micrometeorites, or the early solar wind. Analyzing these deposits could reveal the origins of water on Earth, the mechanisms that delivered life's building blocks, and how planets evolve over time. The moon becomes not just a base for human activity, but a laboratory for planetary history, frozen in time. Philosophically, this changes our perception of the moon itself.